Hi there, welcome to this recording of a presentation I gave at a virtual private conference. The first minute or so wasn't recorded, so this introduction is being added after the fact. The talk is about a statistical method called Approximate Bayesian Computation, ABC, and I look at some examples in insurance. This is joint work with Pierre-Olivier Goffard at the University Lyon 1, where I'm based. I'll show you the problem that we had that led us to ABC being the solution. We looked at a classical insurance setup where we have a random number of claims in some month n, and the size of the claims is also random, u1 up to un. We've decided on some parametric model for these distributions, and they have theta parameters for each of those separate distributions. And we'd like to fit them, but we don't actually observe these data directly. We see some kind of aggregate of the data. For example, for each month we might see the total sum of all the claim sizes, or we might see the value of the largest claim, or a stop loss premium, which is a kind of censored version of the sum of the claims. One idea we had for this was to think about an insurer handing over some details of their portfolio to a reinsurer, but not giving the reinsurer all of the details. And so then the reinsurer has to understand the risk involved from only this partial observation. So our question is, given this sample x1 up to xn, how do we find the theta parameter which best explains them? An easier variation of this problem is when we have these summaries x1 up to xn observed, as well as the number of claims n1 up to n small n during each of the periods. So I'll just start off by saying that this question is more or less impossible to solve. The first question is it's not exactly like this, but it's kind of like saying, I have some numbers and they add up to 10. What were those numbers? So of course that's impossible. The second question, which is slightly easier, is kind of like saying I add up 5 numbers and they add up to 10. What were those 5 numbers? So just to put that in a bit of context, the main key idea about getting into this ABC method is to look at likelihoods. And they say ABC is a method that you use when you don't have access to a likelihood. And so I might just quickly mention what that actually means in practice. So simple random variables, we know their likelihood, their probability density function. So the normal is the bell curve and exponential, so on. But as soon as you start doing things to these simple random variables, you come up with more complicated things which model reality better, but we no longer know the likelihood. So a really simple example, taking 2 variables which are IID from some distribution and you add them up. Most of the time that resulting thing doesn't have a likelihood, but from very special cases, we just can't solve the math to get the likelihood. So in that one case where we don't have access to the likelihood. A more general case is sort of a practical concern. So imagine that we have some observations. Their likelihood is the product of the individual likelihoods. And these numbers are small. And when you multiply small numbers, the computer often sort of stabs you in the back and just returns the number 0. So that's another way we can say that we kind of don't have access to the likelihood. Or similarly, if it takes a very long time to calculate each one of these likelihoods, that can be enough to make likelihood inference impossible. So we'll be looking at this problem from the viewpoint of Bayesian statistics, and so by that I mean we start off with some idea about the answer before we see the data. We see these thetas as random variables, and this thing on the left here is just an example of a prior distribution. So imagine this problem where if we flip a coin and we say, what's the probability of this coin's coming up heads, even without seeing any data from this and seeing some coin flips, I already have a pretty good idea of the probability of coming up heads. Like most coins in the world are about 50-50 chance, with some small variations at the very end for these double-sided coins. So the prior distribution is the first element for this, and the posterior is the updated form of the prior given some observations. This is what we'll be trying to solve for. So if you had a likelihood, then you would go ahead and just run a Markov chain Monte Carlo example. I'm not going to talk about MCMC here. I'm just plugging here some videos on YouTube to try to boost my subscriber count. The second video here is something I made for my students about fitting the incubation time of COVID-19 using Python's PyMC3 library, which I thought might be of interest to this audience. So to get onto an example of what ABC looks like in practice. So we'll go back to that coin flipping example. We'll say that we have some coin, we flipped it 3 times, and we saw heads, tails, heads. And we have to look at just the probability, theta being the probability of it coming up heads. So one Monte Carlo kind of way to do this is to start off by choosing a random candidate theta prime. So here we started off with 0.94. So we picked a coin which comes up heads 95% of the time. And then we go ahead and just start flipping that coin. And so here I've written this as it came up as heads, heads, heads here. And if we do this process and we get an outcome, some fake data, as I'll call it, that happens to coincide exactly with the observation, then we'll keep this as a sample from the posterior. So this one didn't match the observed data. But this third time we tried this process, we got a heads, tails, heads. And so we keep this theta prime, which generated it, the theta is 0.053, as a sample from the posterior. And allowing this process to go on, if we do this 100 times, we accept about, let's see, about less than 20 samples that are from the posterior. And we can make, this is what is shown in the histogram here, and in the KD above it. So, I don't think anyone calls it by this name, but I'll call this the exact matching algorithm. So we have some observed data, and what we do is we start with our prior distribution, sample some potential theta from that, use that to generate fake data, and if the fake data is the same as what we're trying to fit, we store that theta prime as a sample from the posterior distribution. So, of course, that you can imagine it's quite unlikely for a match to actually occur. So, looking at the exact same problem, except now the data is a bit larger. Our observed data is these 8 coin flips, and writing this algorithm 100 times, we never randomly come across a coin and then some fake data, which happens to exactly match the observation. So we become a bit more lenient. So instead of having an exact match, we look for fake data, which is pretty close to the observed data. So in this example, what we're doing is we have this observation here on the left, which is has 5 heads and 3 tails. We sample from the prior distribution a potential theta, which is 0.55, probability of heads. And then we go and generate some data from that. And the generated data has 6 heads in it. And 6 heads is close enough to 5 heads that we'll accept that as a sample from our approximate distribution. And again, doing this the second time, we come up with some other fake data, which has 4 heads, and we'll also accept that. So in this case, we're accepting 4, 5, or 6 as being close enough. And so this gets around that problem of it being impossible to perfectly replicate our observed data just by randomly guessing it. So we'll accept anything that's kind of close enough, and we'll get an approximation to the answer. So this is the name. What I've just described is called the ABC acceptance rejection algorithm. So, and what is important here is, I guess, that we don't sample from the exact posterior, but we get close to it. We get what's called the either approximate posterior or the ABC posterior. And it depends on how lenient we are about accepting things, what we call close to the observed data. That's determined by our threshold epsilon. So here I'm just comparing the approximate posterior to the real one. So this is for that data I just showed, the real posterior distribution that we're trying to fit. And this is one of the ABC posteriors where we're having an acceptance threshold, which is kind of small, which is 1. And we see it kind of got the right shape of as the true posterior. We're not very far off it, but we're a bit wider, and that's kind of the trend that we'd expect. If we are less and less discerning, and the epsilon gets larger, then eventually our approximation degrades, and this last one is we've accepted everything. Epsilon is infinity, and there's no posteriors here at all. We're just again recreating the prior that we started with. So if you've heard the name acceptance rejection algorithm before in some Monte Carlo class, it probably was on the first class because it's a very fundamental algorithm, but it's very inefficient. You can imagine that your prior distribution doesn't necessarily give samples which are close to the observed data very frequently. So in practice, you'd actually use a more complicated algorithm, a sequential Monte Carlo algorithm, which I won't go in details into, but the main idea is to take one of those rough approximations to the posterior and improve it to make it a better one, and repeat this process. So what does this look like? Going back to that original example, motivation we were considering, we have some claims that are coming as a Poisson random variable. The claim sizes, the sizes themselves of the claims are dependent on the number of claims. So more claims, larger severities. And that'll be characterized by a dependent exponential distribution. We don't observe this though, or we say observe is the sum of the claim sizes. And what is in the plots here are the three posterior, the three ABC posteriors for those three parameters, the lambda for the Poisson and the beta delta for the dependent exponentials. I'll start off by saying in purple is these, we looked at just uniform prior distributions over some range of possible values. And then the blue curve shows the approximate posterior having seen only 50 observations, sample size of 50, and then the green one a larger sample size of 250. And they match, the green one matches very well with the true values, which is the dotted vertical lines that we use to generate the data. So this is a kind of interesting case that having dependence means that we wouldn't have a likelihood in this situation, I don't think. And this is kind of a best case scenario of this working. Quickly compare it to the true posterior. Because we're not observing the whole data, we're just seeing the sum of the claims. This is where the main difficulty of our problem comes in. If we had the whole data, all the claim sizes, all the claim counts, we would just use Markov chain Monte Carlo and get these more peaked histograms here, which is sort of the true posterior. But even though we're not seeing the whole data, then we're still getting quite close, which is quite positive. So one of the outputs, one of the main things that I focused on in this work is to create a highly optimized Python package to work to solve these kind of problems. So, for example, all you would need to do is specify I have a prior that's between these values. My model is a Poisson and dependent exponential, and just call the SMC method. And it'll run some highly optimized Python code that's parallelized here over the 20 of the 40 cores of our server at ISPA. And so the plots I showed a moment ago were generated in under a minute, but to do so, it generated hundreds of thousands of simulations. So I should have emphasized this from the beginning, actually. You use ABC when you can simulate your data, even though you don't know the likelihood, which is many cases. So to show a less stunning result, if we look at the situation where we have negative binomial number of claims, each claim size is widely distributed. But we don't observe this, we only observe a truncated sum. So the sum, if the sum's over the value 6, we observe how far it's over 6. The effect of this is that for our 50 sample size of 50, we only really have 11 values which are non-zero. So, and for 250, only 69 values, which is not very much to work with. And we can see here that ABC's come up with some sort of mixed results. So I'll point out the parameters here are the alpha and p for the negative binomial, and the k is the shape parameter, and beta is the scale parameter for the y-ball. So it seems to have done k very well. It's fine. It's narrowed the prior and is quite confident about k being a small value, which is good. The k is more important than all the shape parameters are more important to get right than the scale parameters, and p it seems to be kind of undecided about whether p is a very large value or a very small value. But kind of a common theme that we've seen in our results is that the scale parameters can be compensate for each other. So here it's kind of coming up with the idea that the frequency parameter, scale parameter is much smaller than it really is, but it kind of compensates that by having the severity scale parameter be much bigger than it really is. So this is some kind of thing that, because we've mashed together all the variables, it's a bit hard to disentangle sometimes. However, if you remember at the beginning, I mentioned that there's the easier version of this problem, which is you observe this stop loss premium value, and also you observe the number of claims which happened in this period. With those two pieces of information, then we get much better results. We can narrow down exactly the parameters that we started with from this wide range. So we don't always know that we never know which model truly generated our data. So here it's just showing something, a bit of a failure where we use the same samples as before, generated from negative binomial Weibull model, but we then tried to fit a negative binomial gamma to it, and it sort of it does as well as it can in the circumstances. But what we'd really prefer is to know that this is the wrong model. And ABC has got, this is one of the great parts of ABC. This is built in to do model selection. All you need to do is you pass it a few candidate models to ABC. ABC will fit them all, and in the process, it'll tell you what is the posterior probability of each of those models given the data. So here's the simple version of the algorithm. You need to supply it with a prior distribution over the models. You sample a theta from this model, and then sample some fake data from this theta. and accept as we were doing before. So in that example that I just showed a moment ago, where we had this data and we used ABC to fit Weibel and to fit gamma, even though the data came from Weibel. Well, we see that the ABC with 50 variables is 75% sure that it's coming from a Weibel model, which is quite good. And given more data, it gets more confident. It says 90-something% sure that it's coming from the true distribution. And then given more information, it gets more confident. Sorry, my alarm for 20 minutes just went off. I had to turn that off. Okay, so I'll finish up now. As I mentioned, sort of my focus on this has been this optimized Python package, which you can see on GitHub if you like. Pierre-Olivier worked on some theoretical contribution, looking at when we have this truncated data, we no longer have purely discrete or purely continuous. It's mixed data, and he did some convergence result related to that data. And that's all I wanted to talk about today. Thanks for zooming in.